Hi, Ethan. We have to wait for a few minutes to have more students joining the class, and then we'll start. Thank you, Ethan. Okay, we have a long summary today, so I think we start and hopefully more students join the class. This week is a summary of the equilibrium conditions. So the keyword for that one is called statics. Statics means a system of forces under equilibrium, and that is simply the first law of the motion. Sometimes in textbook it's called the Newton first law of the motion. So I believe everyone should be familiar with that topic in energy and motion. So first, we summarize the conditions of rigid body, and a very important topic in this unit is called free body diagram, or simply we call this FBD. Equations of equilibrium, like usual, we define that in the two-dimensional case and in the three-dimensional case later. And then we classify the structural members or the rigid bodies as two important classifications. The rigid bodies with two force apply to them and rigid bodies with three force apply to them, which are under equilibrium. And then once we understand all this, the very same concept can be generalized to the three-dimensional case. And then we rewrite the equilibrium equation in three dimensions, and finally we have to deal with friction. All right, so friction is a little bit less relevant to this unit, but we just quickly summarize that here. So first of all, equilibrium means when a rigid body is under equilibrium, some of the forces are equal to zero, and sum of rotations are equal to zero. So what does it mean? I mean, this is best understood when we go through a number of examples. A free body diagram means when you are studying a structure, you have to consider a part of that structure. And why is that? Because if a building is under equilibrium, everything within that building is under equilibrium. Let it be a table, let it be a room, a part of the structure, a beam. So when a big system is not moving, all the individual components are not moving. So free body diagram would let us to choose to isolate a part of the structure and study that in terms of the translational forces and rotational forces. So support reactions, these are the forces which are interfacing several subsystems together. But when we decide to solve a part of the structure, we have to isolate this, we have to release that from its support. And when you release, those internal forces should be exposed as support reaction forces. So again, this is best understood by example. Here, I'm showing you a I-beam section. So this is an I-beam. You have seen I-beam in the structure. So that's the cross section, side view. So that is sitting on a roller. So the roller is preventing that I-beam from vertical motion. Okay. So therefore, if I release that one from this interface, I have to replace that roller with a reaction force. So in another word, this beam is withstanding the forces which are exerted vertically, but that is free to move horizontally. So that type of roller can only offer resistance in one dimension. So not all supports are like that, only roller is doing that. And roller is classified as a contact support. So there is a contact between the roller and the beam. So at the contact, normal to the contact, you develop a resistive force. Now, the next type of reaction we have, this is called the pin support. A pin support is when you have a member which is pinned to another member. So what it means is this structure is free to rotate, but it is confined to move horizontally and is confined to move vertically. So therefore, if I release that one from here, I need to replace that support by two forces. I don't need to put a resistive rotation because it is free to rotate, but it is restricted toward the um, translational motion. Either I would represent the reaction or resistance by two components fx, fy, or I would represent that with one magnitude and one direction. These are equivalent. So these are equivalent. So next type of support is when we have a member fitted into the wall, right? So a member fitted into the wall, if you try to rotate it, it would resist. If you try to pull it, it would resist. If you try to push it vertically, it would resist. So three type of resistance. So therefore, if someone is releasing that structure, separating that from the wall, they need to replace that at the wall with one rotational resistance, one vertical resistance, one horizontal resistance. Okay, so this table is summarizing the type of the support we have. One of them, the most simple one, is when at the end of the rigid body, a cable is restricting it. So it is free to rotate, it is free to move, only restricted along the cable. So that develops only one reaction. When we have a pin support, that pin support either can be replaced by two translational resistance or by a magnitude and a direction. So these are equal. The next type of support is a roller support. A roller support is free to move, is free to rotate, and is only confined normal to that movement direction. So that is, if you release that or separate that from the contact, you have to include a resistive force in that direction normal to the direction of the motion. So the next type of support is a roller or a pin which is confined in a slot. It's free to move inside the slot. It's free to rotate, but um, if I only release the pin release is described by a force and a direction. So this is a contact support. The contact, if I release it at the contact, there would be one force. But if I release it at the pin, I will have one force and a direction. This is a simple contact. With that simple contact, my reaction would be normal to the direction of sliding. So this is free to slide parallel to the surface, but is restricted to move vertical to the surface. Um, Next kind of support we have, this is a collar on a smooth rod, so there is no friction, so therefore it is free to slide, but is confined to move normal to that rod. All these type of support, we give you some examples. All right, so first example here, we have to identify what type of support is here. So if I want to release that one, this is a pin support. This is a pin support. So the pin support would resist either by the horizontal reactions or by the magnitude and the direction. So that this is a cable. I know that through this cable, the resistance would develop only along the cable. So if I release the pin, that pin, um, the reaction force would comply with that cable. So because this pin is followed by a cable, we know the direction of this force. So here, that is a contact. So the contact is, here you have a round edge contacting this surface. So it only resists normal to the contact surface. The next type of support I have here, that is um, this block of concrete is sitting on a step, and as such, that is confined to uh, move vertically, and because of this gap, it is free to slide that way. So this is like a simple contact. So here we have a pin contact which resists in translation. I mean, depending what coordinate system you take, it is confined to translate in this direction, that direction. So this is can be considered as a two-dimensional problem or 3D, depending what are the active forces. So that is a cantilever. So that cantilever. So if we look at this beam, it's confined to move that direction, confined to that direction, and it won't rotate in 3 dimensions. All right. So that has 3 forces and 3 rotations. So that's a 3 dimensional fixed end. The next important concept here is when you want to consider the external and internal forces. So contrary to energy and motion, here we don't consider a system as a particle. A particle is when all the mass properties are lumped in the center of gravity or center of body. But when we are talking about the rigid body, the forces are distributed, they can be applied into different locations, all right? So that is the difference. And then when we are talking about a compound rigid body, which is composed of a members fitted together either by different type of reactions. So you have to isolate them, and before isolation, some of these parts are active between the members. So as long as they are not released, we regard them as the internal forces. But if you want to study the subsystem, only a part of the structure itself, you have to release, and once you release, that internal force would be exposed to an external one. So I give you some example of that soon, but it is important to find out the difference between internal and external. The most common external forces are when you apply a force to a cable, or when you push a point or pull a point or cable. Other example of external force is you put a lump mass on a beam, so that's an example of external force. But internal force, these are the resistance developed at the reactions. Weight and center of gravity. So yes, we are dealing with a rigid body, but when the system is a rigid body, the weight is distributed. Having said that, it is okay to lump all the weight forces acting at one single point, and that single point is center of gravity. So in another word, here you have a rigid body, so it is composed of infinite number of particles. So these particles individually they develop some gravitational force, but the total mass we can lump this one into the centroid, the CG of the part, and that is where the external force W can be simplified, can be exerted at. So sometimes you have to idealize the models. So the way we idealize, this is a good example. So in real life situation, this problem is a 3 dimensional case. But when we want to analyze it, we consider that as a 2 dimensional problem. So the third dimension perpendicular to the paper is not important. So yes, what about the support? The support, I see that here the left-hand side is confined. not only vertically but also horizontally. So that makes a good simplification if I choose that one as a hinge, as a pin support, but the right one is confined vertically and free horizontally. So that is a good simplification if I consider a roller support. And what happens at these three contact points? So I want to get rid of these members, but in action, what they do is the weight of these actions are being exerted at this pin at 3 points. One, two, three. So this is the real world problem. This is the simplified. In many cases, we have to go from the real world problem into the simplified. Or sometimes, as instead of simplified, we call them idealized mode. So we want to replace real world problem with an idealized one. So why do we do idealization? Because otherwise the problem is not solvable. And then that involves in making a free body diagram. Your free body diagram has to be realistic, has to be representative. Otherwise, your solution is not precise, it's not correct. So let's start with the first example. Here I have a simple structure which is subjected to one external force. So here I have one external force and there are three internal forces here. Because this is a cantilever, this is a fixed support, one internal force is here, one internal force is like that, and one internal force is the rotational effect. So I call this AX, this one AY, and this one is MA. So this problem I have to solve, and yeah, that I have to simplify that. So the simplification is I make a beam with that force here, and then this is the external force. Weight is 100 kilogram. 100 kilogram should be exerted right in the middle. So that is 100 times G, gravitational acceleration. So these are the external forces. And then internal forces also should be excluded in my free body diagram. And then this problem is my free body diagram. So this free body diagram, I can impose the condition of equilibrium or the static condition to find out the internal forces or the reactions AX, AY, MA. So yes, how do we solve this? Yes, and then in that example, yes, the 1000 and mg they don't act at the same place because this force is um, acting 2 meters from the left edge. But if I want to include the weight, that weight has to be into the center of gravity of the beam. And center of the gravity of beam is 3 meters away from here. So that is why the W external force weight and external force 1200, they are not exerted at the same point. They would be exerted at different places. But then the internal forces at the left, we just release them. This is like I'm cutting this, isolating the beam from its universe. And when I cut this, all these internal forces should be exposed and included in my free body diagram. So here I managed to convert a real life problem into the simplified. Hi Nima, please make sure you watch the part of the class that you missed. And just for your information, I'm recording the classes so you always can go back and watch the recorded sessions. Thank you, Nima. Yeah, that's fine. No worries, Nima. Recorded lectures can help you, and if you have questions, just email me your question. I'm taking your question and trying to answer them. All right, so next example here, that is a foot-operated pedal. That foot-operated pedal is a part of a mechanism inside the structure. So, of course, we can't study the entire mechanism, the entire system. If we want to study that, we need to release that pedal from its universe. So one releasing point is at this pin, one releasing point is here, and one releasing, that pedal should be isolated from the foot. So the foot is exerting a force here. This pin is exerting a force along the spring. That pin is exerting a force along that rod. And what about A? A is a pin support and it develops two type of reaction, horizontally, vertically. It makes a resistance horizontally, vertically. The foot would exert a force normal to the pedal, and at this point you have a spring load, which is um, so let's have a free body diagram of the lever. So if I release that, I know that to release the force, that is an external force which I apply normal to the surface. That's a contact. So it's not offering any resistance. It is friction free. It's free to slide, but it resists vertically. And at point A, because this is a pin support should be, after releasing, should be replaced by two external forces or two reaction forces vertically, horizontally. But a spring only exerts a force axial to the spring. So that is, we know that this exerts 200 Newton. How do we know that? This was given in the problem set. And then the lever. The lever is resisting 100 Newton. So what do we want to find? We want to find how much force is being exerted by the foot and what are the reaction force. So this is unknown number one, unknown number two, unknown number three. So that is called a free body diagram. So from now on, we have to go from the real life problem to the free body diagram. And this is a skill. This is a skill. To do that, you need to know the support type. So one support type is being used here is a cable. So this is like a cable or rod. That is one type of support. A spring is very similar to the cable. They only exert a force axial to the member. So both of them, they only develop an axial force. The second type of support which we use here, that is a hinge. So a hinge develops two type of forces, vertical, horizontal, and finally there is an external force exerted by the foot, which is a contact. So here, how many type of support we have? This is cable or link. This is cable link. This is a pin support, and this is a contact support. All right. So now this free body diagram should be solvable, and how to solve it, I think we catch that later on. All right, but at this stage, you should be able to draw or to make the free body diagram. Free body diagram is the most challenging part in this subject, and you would master it only after doing enough practice. So we have a number of solved problem in the class. We do have a number of worksheets, and once you do them by practice, you learn about how to make a free body diagram, how to solve a free body diagram. So that is the main part of this subject. It requires some judgment, and you only can make those judgments by experience. Practice makes it perfect. The more practice you do, the easier for you to make a free body diagram and to solve them. So free body diagram could be your best or worst, best friend or worst enemy. You decide which one you want this to be. Hopefully you can master it in no time by doing enough practice. So that is the next example. Here I have a forklift. So the forklift is holding one, two big pipes. So the first question is whether this is a two-dimensional problem or three-dimensional. So we reduce this problem into the two-dimensional because the dimension perpendicular to this page is not important. So I see that these pipes are contacting each other. So this is a contact point here. There is a contact point between pipe number one and the fork, pipe number two and the fork. So what forces are involved here? There are gravity forces. So each pipe, if you want to release them, if you want to make a free body diagram of the pipes, I can either make a free body diagram of the two pipes together, right? So I can study this one, or I can study the free body diagram of pipe number one, pipe number two. So in this case, I don't need to worry about the contact force here because this is not released. But if I make a separate free body diagram, I do need to know the contact forces when I release them. So in this case, the internal forces should be exposed to the reaction forces. And what other reaction force? Here, I have a reaction force normal to this one, normal to this one, right? And what is missing is the weight of this pipe here, weight of that pipe here. In that case, I do need to have a reaction normal to this one, reaction force normal to that one, and one gravitational force here, one gravitational force over there. So here I do have free body diagram 1, free body diagram 2. Here I only have one free body diagram. And how these free body diagrams are developed. So here we start with the individual free body diagram. I call them pipe A, pipe B. Pipe A, like I said, it has a contact from not only pipe B, but also from that side here. So here we missed one contact force because this pipe is not only in contact here, also in contact from here. And then that R is the reaction between pipe A and B, and the external force, the gravity of the pipe, is exerting at the center of gravity. So this is one free body diagram for pipe A, and we can do the similar free body diagram for part B, or we might decide to keep them together. And if we keep them together, then the free body diagram would be a compound one. That compound is composed of A plus B. So you could have A separately, B separately, or A plus B altogether. So your turn. Now we have a platform. That platform is suspended off the edge of an oil rig. So this is a very common structure in a oil excavation sites. So a platform is there. This is like an elevator. People want to go up and down. So you have to simplify this structure. The first question is whether you want this to be two-dimensional or three-dimensional. Okay? So two-dimensional, three-dimensional is dictated by few things. One of them is the nature of the loads. So in this case, all the loads are vertical and all reaction forces are within the plane. So this makes a perfect two-dimensional case. But if someone was shooting at this platform perpendicular to this page, then you did have forces outside the two dimensions, and in that case, the problem should be considered as a three-dimensional case. But in this case, we have every reason to convince that this is a two-dimensional problem. So let's make this a two-dimensional problem. I make a platform watching normal to the plane. So I do need to separate this from this cable. Here I have a hinge. This is a cable, and I think that that's all. So at the hinge, I do have two reactions. Let's call this A. So this is AX, this is AY. And because I'm cutting this cable, the cable is a type of reaction axial to the cable. And what is missing? That is the weight of the platform. The weight of the platform should be exerted right in the middle. So that is the free body diagram for this platform. So what is W? W is calculated as 400 kilograms multiplied by 9.81. That's the gravitational acceleration, and the unit is Newton. Okay, so that is the free body diagram, FBD, for the platform. Yeah, of course, the location of this external force is important, and that is because when you take into account the rotation, all you're dealing with a rigid body, you're not dealing with a particle. So back in energy and motion, you used to deal with particles. Maybe rarely you did the three rigid bodies, but here everything is about the rigid bodies. We are not considering the particles anymore. Real life situations, most of the cases, the free body diagram is related to the rigid body or rigid systems. So next example, here we have a plug, or this is a beam, which is what type of support are here. So the first support here, that is a hinge, this is a pin support, and that is a contact support. So at the beginning of the lecture, we summarized the different type of the support. And then we remember whenever there is a contact, if I have to make a envelope isolating this system from the universe, anything inside the envelope, that is my free body diagram. Anything outside, that is the universe. Free body diagram would only look into the interaction of the forces inside the free body diagram. And because I'm releasing this support, that support, the internal forces should be exposed as the reaction. So with the pin support, the reactions are two vertical horizontal. That means the pin is preventing my system to move vertically or horizontally. So when I release that support, which is a contact support, it's free to slide parallel to the surface, but is confined to move perpendicular to the movement direction. So that internal force, I expose that as the reaction normal to the surface, so that is RA. And at this point B, because this is a pin support, it develops two type of reaction. And here I have my free body diagram developed in the two-dimensional case. So like I said, this chapter is all about making free body diagram, heaps of examples, and more example I hope Greg would do for you in the class. So yes, that is a two-dimensional free body diagram we developed for this simple structure. All right, so what do we do when we develop a free body diagram? What is the next step? The next step is you have to solve the free body diagram. How do you solve the free body diagram? Yeah, free body diagram is only 50% of the task. The remaining 50% is to solve it. So it's not good enough to develop a free body diagram, even though my free body diagram is correct, but it is also as important as how do we solve this. So to solve the free body diagram in order to find the unknown reactions. Why should I solve the free body diagram? Because I want to understand, I want to identify the reaction forces. So that is the next step. So up to now, we learned about the different type of the supports, different type of the reactions, whether the problem is two-dimensional, three-dimensional, and how do we idealize the system. From now on, we want to understand how this system of forces can be solved because not every force in this free body diagram is known. Let's go back to what free body diagram. So here, yes, we don't know how much the traction is. We don't know how much these reactions are, right? So this is a known value. This is a unknown number one, unknown number two, unknown number three. So in this problem, we have three unknowns, right? So let's go back to here. In this free body diagram, how many unknowns? One unknown here, two unknown there. This is a known value. In this free body diagram, one unknown, two unknown, three unknown. And this is given values, ungiven values. So with every free body diagram, there are some values which we know, and there are some values which we want to identify. So that requires a solution. How do we solve that? We solve that by the first law of the motion, Newton law number one. And the rest of this lecture is about explaining the condition of the equilibrium. Condition of equilibrium or equations of equilibrium, these are the recipes, these are the guides for finding the unknown forces. So that is nothing new. We already know that from past. So let me run this video for you.
Let's try that. This is a not. Hello again. It's good to be back with you. One of the first questions people have to answer when they start studying statics is how to solve for the reaction forces on a beam, particularly if that beam is loaded asymmetrically. That means if the load's not in the center. All right, so let's try that. This is a not too hard to do, and it's especially easy if you follow the solution process for all statics problems. And I'll tell you about that in a second, okay? So let's say this is a pinned beam. Now, pinned means the ends are free to rotate, okay? Now we draw this assuming there's this little triangular base with a pin on it so the beam can rotate. Well, how often do you actually see those? Well, maybe more than you think. You'll see these on road bridges. When you drive under them on the highway, you'll actually see things that look surprisingly like that. But it could be like a floor joist just propped up on its ends. That still counts as a pinned beam. So let's say we have a beam, and let's say it's 3 meters long, okay? And let's say that there is a grading professor standing on it, and that grading professor weighs 900 newtons, and let's put the center of his load at 1 meter from the end of the beam. So it's 2 meters there, 1 meter there. I don't quite have it to scale, but you get the idea. And I got to call these ends something, so I'll call that A, and I'll call this B. All right? So given that, the solution is find the reaction force at A and the reaction force at B. Okay? So obviously, when you're standing on the beam, there's a part of the weight is being supported over here, and part is being over here. Since the load is not in the center, it makes sense that those two wouldn't be the same. All right? So what we're going to do is we're going to draw a working diagram, which we just did. Okay? Next, then I'll get out of your way here in a second. Then we're going to draw a free body diagram, which I'm going to do up here. We're going to write out the equations of equilibrium. Okay, that's kind of a 50-cent way of saying some of the forces equal zero, some of the moments equal zero. That's really what this means. And the last one is that we're going to solve those equations to find something we need. So we've already got that one. So let's draw a free body diagram. Okay, free body diagram is a simplified version of that. It's got all the parts that are necessary, but with none of the other complications. So it's a little more conceptual. So here's what we've got. This free body diagram is pretty easy. There's force up at B, force up at A, and the force down here from the load. Professor standing on it. We've got to have a coordinate system. Okay? Now, you can pick any coordinate system you want. Whatever one you pick, you probably want to use the same one most of the time. I use this one most of the time, unless I've got a pretty good reason not to. You know, if something about the problem is at an angle or something, I'll change it. But if you use the same coordinate system all the time, you tend to mess up less. So that's good. So now we've got a free body diagram. That's good. So we've got this over here. So let's see. That's step one. That's step here. That's step one. That's step two. Step three is we're going to write out our equations of motion. Okay. Now you remember, statics doesn't have a lot of theory to it. Okay. The theory is explained to me by a great professor here at Purdue. Was sum of the forces equals zero, sum of the moments equals zero. You can't push a rope. Everything else is detail. Okay. So let's do this. Let's say the sum of the forces in the y direction equals zero. We don't have any forces in the x direction, but if we did, we would have another equation here. So let's see, FA is positive plus FB minus 900 newtons, and that's zero. Now, I drew those forces up because it's pretty obvious they have to be vertical or else the beam would be moving. If you guess wrong, if you guess the wrong directions for FA and FB, don't sweat it. The math will take care of you, and it'll give you a negative number for a force. That's math's way of telling you that you drew the force in the opposite direction that it's actually going. So that's okay. If you guess wrong, math will take care of you, assuming you do it right. Now, I got to sum the moments about somewhere. Well, it doesn't really matter where. The equation is valid no matter where I sum the moments. So it's good to sum the moments in a location that makes the math as simple as possible, makes the resulting equation as simple as possible. Let's solve it at A. Let's see, if you want to pick something else, go ahead. It'll be fine. But that has to be zero. Now, the moment about A, remember about that point there, this 900 Newton load is going to make a moment in the clockwise direction. Well, that's against this coordinate system, positive assumed coordinate system. So that's going to be a negative moment. So I've got minus, it's going to be in Newton meters. So 900 newtons times, that's going to be 2 meters right there. If that's 1, that must be 2. Times 2. How if I do an x there, the times there? And then I've got this moment up here. Now, the moment due to the force at B, back in the frame, due to the force at B is positive because the moment it creates about point A is counterclockwise, just as the positive sign convention says. So I'm going to say that's was 3 meters times FB. I don't know what FB is yet. But look at what I got here. I got one equation and one unknown. So solving for FB isn't going to be very hard. So, okay, so we did number 3. Last thing, number 4. Okay. Last thing is to solve our equations of equilibrium. And we've got working diagram, free body diagram, equations of equilibrium, and then solve. And this is the same for every statics problem. They all follow this process. Okay? So let's solve this one first, since that's easier. Let's see. If I say, let's see. If I write that as 1,800 Newton meters, 100 Newton meters equals 3 meters times FB. I'm gonna make it an X there. I gotta make it an X there. Okay, and that's FB. That's terrible, but there you go. There's FB. Well, I divide through by 3 meters, and I'm going to get 600 newtons. Because remember, units cancel out just like numbers cancel out. That turns into 600. All right, and I'm left with newtons. Okay, does it make sense that the load at B the reaction force at B would be higher than the reaction force at A? Yeah, it does, because I mean you're standing closer to that end, makes sense that this end would have to bear a greater portion of your load than that does. Okay, so we got that. Last thing to do is plug FB into that equation right there, and we'll find that FA is 300 newtons. Okay, so there's your two solutions. There's the last step. Now, just to double check, when I add up those two numbers, I probably should here, I'll write this here. This will appeal to my sense of symmetry here. Oops. Yeah, that's right. Okay, there you go. Does it make sense that that number plus that number is 900? Well, yes, it does, because that's the load. Now, notice I didn't put a weight, I didn't attach a weight to this beam. I'm assuming the weight of the beam is so light that its weight of the beam is small compared to the weight of the person standing on it. Okay. Well, maybe that's true, maybe it isn't. If it isn't, and the beam is uniform, that is, it's the same everywhere, you can add another weight in the middle there to account for the weight of the beam and solve again. All right. So there you go. We've drawn a working diagram, drawn a free body diagram.
Okay, so that is in simple term explaining how do we go with the solving it. And to solve we need equations. So how many equations we have, this is a matter of dimensionality. So in the two-dimensional case, there are three conditions. One condition is the system doesn't move horizontally. The second condition is the system doesn't move vertically. And the third condition is the system doesn't rotate. All right? So simple. One, two, three conditions. So three conditions, it means in the two-dimensional case, I can only handle three unknowns. So three is the maximum number of unknowns I can handle uh, in the two-dimensional case. But if that's a three-dimensional case, I can handle six unknowns. And then this is very simple. I mean, I can show you mathematically that when we are saying some of the forces are equal to zero, because the force is a vector, and vector in two dimensions has only two components. So that I say sum of the force equal to zero, that would resolve into two equations, equation number one, equation number two. And then when I say sum of the rotation equal to zero, that is only the third equation. Hi Flynn, nice to have you in the class. So please note that all classes are being recorded. So whatever you miss from this class, you can go back and watch this using Collaborate Ultra. And all lectures on Monday, Flynn, will be recorded, but the classes with Greg, I don't think they are being recorded. All right. So I made some offline version of the uh, not only lectures but also the tutorials run by myself. These are recording from last term. If you don't have access to the last term resources, you can get these offlines. Just let me know. I make a way of providing those recording for everyone. All right, that just keep in mind. And now we go back to where we left. So we're talking about the equation of equilibrium. So far we learned how to make the free body diagram. So in the two-dimensional case, the free body diagram would result into a maximum of three unknowns. So three unknowns, three equations, one, two, three. So that is the maximum we can handle. Anything beyond that, the problem would not be solvable, right? So yes, this could be the case. In many cases, even in two-dimensional case, we might not be able to identify the forces if, according to whatever the free body diagram we have, if there are more than three unknowns, we are not able to solve that. Okay, so that is the simple example, very similar to that I just demonstrated to you through the YouTube channel. It's very similar, except the numbers are different, everything else is the same. So let's just skip that one because this was covered in the YouTube video. And the next thing we have is we go with the state of statical state of a beam. So a beam, what kind of support a beam has? A beam might have a contact support, might have a pin support, might have a fixed support. And then we are familiarized with this. We are familiar with these supports. The contact develops one reaction. The pin develops two reaction in two-dimensional case, and the cantilever or fixed end develops three reactions. So these are the examples. I mean, that is a simply supported beam. So one end that could be a contact only develops one resistance toward vertical. So this is a pin support. The pin support develops two reactions. It doesn't move vertically, it doesn't move horizontally, but the roller support is free to move horizontally, restricted vertically. And that's a cantilever. The cantilever resists horizontal, vertical, and rotational motion. And that is an overhanging beam. So overhanging beam has a pin support here, a roller support over there. So these type of problems, these are called statically determined beams. Why determined? Because either of these problems have a maximum of three unknowns. Three unknowns. One, two, three. One, two, three. One, two, three. So when there are three unknowns, we have three conditions. Condition one, condition two, and condition rotation, right? One, two, three. So this is determined problem. It means we are able to solve them. But let's have a look at some tough problem like this one. Even though they are two-dimensional problems, but this one has one, two, this is a roller, three, that is four. So here we have four unknowns and only three equations. So this is not solvable. We call this indeterminate. This one is not solvable too, because you have one, two, three here, one, two, three here. So that is a six unknown, and we only have three equations. So that is not solvable. This is indeterminate. And what about this one? That one is restricted horizontally, vertically, rotationally, and at the end is a contact. So that's one, two, three, four, and we only have three equations. So that is not solvable. That is called also indeterminate. All right. So when we have a two-dimensional case, how do we solve this? We apply the condition of equilibrium, and then this both, this is a two-dimensional case. Only x, y, and the rotation. So three equations. But if we jump into the three-dimensional case, things become crazily complicated. So we postpone that one to the last topic. So because we try to understand this using the two-dimensional case. Once we understand that, it easily can be generalized to the 3D case. So now that's a slightly different problem, and the only difference is to the problem I solved before YouTube. It is not just one external force, one external here, one external there, and then you have a y, ax, and the reason is this is a pin support. The pin support develops two reactions, and that's a roller support. The roller support only resists vertically, so b of y. So the first question is this problem solvable? Let's find out the answer. One unknown here, two unknown here, three unknown. And how many equations? We have equation net forces horizontally, net forces vertically 0, and net rotation 0. So that problem is solvable, and let's try solving it. First step is the free body diagram. So the weight is being neglected. I ignore the weight, and in next slide I show you the same free body diagram. So how many unknowns? 1, 2, 3. So this problem is solvable. So how do I go about the first condition? Net forces horizontally equal to 0. This system only has one single, that is my coordinate system, x, y, and rotation, m. So the only horizontal force I have is ax. So ax is equal to 0. That is the first solution. The second condition is net forces vertically equal to 0. And ay is positive, 10 is negative, and 5 is negative, and by is positive. So I can't solve this equation because this equation has two unknowns, ay, by. I can solve this one. But wait, now I have the third condition, which is a rotational condition. And I have to write the rotation with respect to a point. Which point do I take? Do I take it B? Do I take it A? Do I take it here? It doesn't matter. You can take the rotation center everywhere you wish, because if a system is at equilibrium, it would be at equilibrium with respect to any point. It doesn't matter what. But because we are smart, we have to make a smart decision. To me, the smart choice is to make the rotation with respect to the A, because that would simplify the problem the most. Because if I take some of the rotation with respect to the A equal to 0, I don't have to worry about AX, because both of these two forces are colliding at A. And if the forces are colliding at a rotation point, they are not capable of rotating the system. Does that make sense to everyone? Imagine you have a disk, and this disk is fixed at the center. And if you apply a force which is passing through the center of the disk, it won't rotate the disk. If I apply a force which is here, that has capacity to rotate the disk. But if my force is exerted like so, because it's passing through the center, it won't rotate the disk. And for the same reason, these two forces won't make any rotational effect here, and they would be excluded in this equation. The next one is 10. 10 makes a rotation. Imagine this is a poster, and I have fixed the poster at point A. I put a pin at point A, and now my poster only can rotate about point A. So how does this 10 would behave? 10 would make my poster, which is pinned at A, to rotate counterclockwise. Clockwise, according to this convention, is negative. So the magnitude of that rotation is 10 multiplied by these 2, so negative, minus 10 times 2. 5, the arm of rotation is 2 plus 2 is 4. Again, that's a clockwise negative, minus 5 times 2 plus 2. And eventually, by it makes my poster to rotate counterclockwise about A. So A pinpointed to the wall, so the poster rotates clockwise due to by. So that is plus by, but the arm of rotation is 1 plus 2 plus 2, which is 5. So that is equal to 0. This equation is solvable because it only has one unknown, which is by. So by solving that, I find by, and once I find by, I bring that by back to the previous equation. And now, instead of two unknowns, I will have only one unknown, which is ay. So that would result in finding ay. All right. Anyone is happy with this solution, or do you want me to explain again? All right, let's move on. Here you have access to the detailed solution. Next example is a more complex one. And here we have a beam which is supported at the right by a pin support. And I know that the pin support will develop two reactions. At the right, I'm not concerned at this point. This point is a pin point, but the contact of that roller with the ground, that is a roller couple. So that roller would only develop a reaction. I mean, if you look at that roller itself, Yeah, here there should be two reactions, but then one contact here. So therefore, the horizontal should be zero. A is one, two, three. And how many external forces? So one external force is this one, for which I have the magnitude and direction. So I can resolve that into two components. And one external force is 100 Newton applied here. So summarizing this free body diagram, we do have one, two, three unknowns. How many conditions we have? We have three conditions. The system doesn't move horizontally, the system doesn't move vertically, and the system doesn't rotate. All right? So three conditions, three unknowns, the system should be solvable. So if you start with equilibrium of forces horizontally, I can see that this horizontal component should be equal to bx. So the first condition would tell me that bx is equal to 600 times cos 45. So that I consume one equation. How many equilibrium conditions is left? Two more. So the second one is equilibrium into the vertical direction, which is not solvable at this stage because that would engage two unknowns, ay, by. So maybe I start with the rotational condition. So which rotation condition would you choose? Which one is the smartest one? To me, if I take the rotation with respect to the B, that is the smartest choice because at the same time, one, two, three, four forces are passing through the B and they would not make a rotation. But by the way, 600 cos 45 doesn't pass through B. It has an offset of 0.2 meter. So that means even that horizontal force makes a clockwise rotation, which is a negative one, right? So still, point B is the smart choice for the rotation because at the same time, one, two, three forces do not make any rotation, and only 100 makes a rotation in a positive direction counterclockwise. This one is make a positive rotation counterclockwise with respect to here. That one makes a negative direction, make it clockwise. This is counterclockwise, this is clockwise rotation. And what about A? A with respect to the baby makes a clockwise, which is a negative rotation. What is the arm of rotation of this force with respect to the B? The arm of rotation is 2 plus 3 plus 2, which is 7, 7 meter. And what is the arm of rotation of 100 with respect to the B? That is 2 meter. The arm of rotation of this force with respect to the B, that is 3 plus 2, which is 5. So simply we apply three equilibrium conditions to this problem, and that the problem is solvable because three unknowns, three equations. So let's solve the problem for this case. So this case, I give everyone 5 minutes to solve. So please grab a piece of paper, try to make a free body diagram for that. We already made a free body diagram in the um, previous slide, but just practice it yourself. And then from there, we see whether this problem is solvable and whether we can solve this. Just 5 minutes, please grab a piece of paper and try that. And just we take it from there. 5 minutes. All right, so let's try this problem together. Here we got a beam which has kind of relatively complex supports. So one support is pin support, the other one is a roller contact. So the first step here is to make a free body diagram of that. Right, so let's do this together. So I do need to make an envelope. So the first step is the free body diagram. First step is free body diagram. How do we do that? I do need to make an envelope. So this envelope should release my structure from its universe. So that is how I release that. I'm releasing this from this point, that point. So let's use a letter. I call this one A. I call this one B. So at point B, I'm releasing that, making two reactions because this is a pin support, right? And at point A, that is free to slide along the surface, restricted to move normal. So that I put a reaction force normal to that surface. And what about the external forces? The external forces, I resolve this external force into two components here and one external force here. So that is my free body diagram. And then, yes, so this one is a known values. This is a known value. So one unknown, two unknown, and three unknown. So three unknown values, and then how many conditions I have? I have one condition restricting forces moving horizontal, one condition restricting forces moving horizontal, vertical, and one rotation prevent zero rotation. So one, two, three equation, three unknown. So this problem is quite solvable, is determinate, and then you can apply these conditions. Just for example, if I take rotation with respect to point B, if I take rotation with respect to the B, 27 makes a negative rotation, that is minus 27 times 1.5. These two reactions, point B would not make any rotation because the forces are passing through the center of rotation. That force doesn't make a rotation, it passes through B, but the vertical makes a counterclockwise, which is positive. So that is plus 54 sine 60. That is the component, and the arm of rotation is 3. And finally, this force is making a rotation. But then I need to break that into two components. So the horizontal AX does not make any rotation, it passes through here. AY make a rotation, and that rotation is negative. So that's minus AY, and the arm of rotation is 3 plus 3, which is 6. So here, that equation gives me AY, and then I apply two other conditions to find AX, BX, and BY. So still we have plenty of more summary slides. The next type of a structure we want to study, that is a pulley. So what you need to know about the pulley system is you either can isolate the cable or you can isolate the pulley. It doesn't matter. Either way, by making isolation of the rope itself, you find out that the traction on both sides of the pulley are equal. So that is a recipe you remember from now on. Whenever you are solving a pulley problem, make sure you take tension on both sides of the rope equal, no matter what the angle. It could be that the cable could be parallel, the cable could be at an angle, but always if there is no frictional to the pulley center, That means the tension on both sides of the pulley. In this problem, tension is equal to 500 Newton. All right. So the proof is simple because that distributed load, these pressure forces all passing through the center, they won't make any rotation. But that T multiplied by the radius is equal to 500 multiplied by radius. You cancel the radius from both sides of the equation, and as a result, you get 500 T equal to 500. Don't worry about the proof. In the exam, you won't be asked about the proof, but just all you have to remember is whenever there is a frictionless pulley, the tension on both sides are equal. So now that is the next problem like we want to solve. And then here you have a support, which is the cable. The cable tension is parallel to the axis of the cable. This is the pin support. It develops two reactions. This is a contact support. Contact makes one here. The only point in this problem is you have an external bending moment. So external bending moment, when you are writing the equilibrium equation, the third one, that should be included into the equation with a negative sign because it's a counterclockwise rotation. All right, so now we have the solution for this one. Just please make sure you read the solution later on. And with this problem, yes, you have to make a free body diagram. And then here, because you are trying to loosen a bolt and nut, there are some friction involved. That friction makes this one to act like a cantilever, like a fixed one. So not only you have to worry about the horizontal vertical reactions, also there is a rotational resistance which you have to overcome. So when you develop this free body diagram, you end up with external forces are given. These are not unknown. The only unknowns are 1, 2, 3. And how many conditions you have? You have three conditions, three unknowns. So this problem is also solvable. So this is the solution. I encourage you to go through the solution itself. And now we have half an hour to cover how this concept can be generalized to the 3D problems. So let me give you a note regarding the 3D cases. So with 3D problems, they are only uh, for the mid-semester test. You don't be question about the 3D system in the final exam. But for the mid-semester, unfortunately, there would be few questions from that. Later on, I will post you some hints regarding the what you expect in the mid-semester exam, and we go through some preparation for that. For now, don't worry about this. Um, yeah. So, what difference does it make when you have a system of three-dimensional forces? Still, the object has to be isolated. Instead of an envelope, you have a three-dimensional envelope in which your free body diagram is formed. So it could be an object isolated, two objects together isolated from the rest of the universe, but eventually you may end up with more unknown because the problem is three-dimensional. So this requires for us to understand what type of supports are there. But more importantly, I want you, I want to take you through the definition of what is a two-force member and what is a three-force member. Please listen carefully. This could save your life. This could be very important for your mid-semester test. So here I have a simple bar. So this bar is being pulled by someone from right hand side, someone from left hand side. And then this is how my rigid body, so this is a rigid body. And I call this a two force body or two force member. And I call this a bar. So it has many different names. So make yourself familiarized with two force bar, two force member, bar. And then in all these cases, the system for equilibrium, yes, you can take your x-axis parallel to the axis of the bar. So F1, F2. So for the two force members, we know that F1 should be equal to F2. That is a very simple problem. In another word, a two force member is a special case for which we don't bother to write the equation every time. So as a recipe, we remember that whenever there is a two force member, the forces are acting axial. So this is the axis of the object. So I call this axis. So whenever there is a two force member, the forces are only acting axial. I mean, it is impossible to have a two force member at equilibrium like this one. This cannot be the case. Why? Even though if even if F1 is equal to F2, but this system does not stand still rotationally because these two forces are parallel. They keep rotating and rotating unless you have a couple canceling this rotation. If you have this couple, this is not two force member, that is a three force member, right? So the only scenario that a member with two forces is at equilibrium is when the forces are acting axially in opposite direction with an equal magnitude. So that is the summary of the two force member. So it is important to recognize when you see a two force member. I mean, this is not the only case. Imagine that I give you a boomerang. So hopefully everyone knows what the boomerang is. So this boomerang has two exertion points. So this is a bent link, but with this bent link, what we do is we connect these 2 points together. And now that I connected, I know because this is a two force member, the forces can only be pulling out or pulling in. So that is also a two force member, and it should have two forces which are equal with opposite direction, either making that apart, making this under tension, or pushing this out, pushing this in, making that in compression. All right. So that is a two force member. This is a two force member. So you need to understand what a two force member is. When you see in a real life situation, are you able to recognize a two force member? That is critical. So the next classification, these are again a special solution. When an object is subjected to three forces. So imagine that I have again, I might have a object of any shape, but this object has three exertion points. So it is released from its universe, but it has one force acting here, one force acting here, one force acting here. So how do we deal with this? Is called the three force member. Three force member. With the three force member, the forces have to be concurrent. What does concurrent mean? It means the three forces should collide at one single point. So let's say this is a single point. The only way three force can be at equilibrium is if that force and this force are colliding at this point, right? So these 2 points are colliding here. Right, these 2 points are colliding at this point. Then this is F1, that is F2. The third point has no option but to pass through here, right? So this point should also pass through here. So that is the recipe for three force member. Three force member, there are three forces involved. These forces are concurrent. They are colliding at one single point, or they call this convergent. They converge at one single point. So that makes the solution of three force members simple. If you don't know this rule, you may not be able to solve the problem involving three force members. So two type of members we classified here. The first one is a simplified bar or two force member. The forces are opposite, equal size, and axial. Three force members, the forces are concurrent. They're converge. So in a vector sense, you have F1 plus F2 plus F3 should be equal to 0. So here you solve that by law of the triangle. So that is F1, this is F2, and this is F3, right? So please remember these two special cases, two force members, three force members, and yeah, that's, now I try to give you some examples. These are examples of two force members. So that is just axis. Here the axis is the connecting point between A and B. So why do I say two force? Because it only has two exertion points. If there was a point here exerting another force, that was a three force member. But in this case, even though that's not a straight, the axis is defined as the line which connects point A and B together. Even though this member is a bent one, but it's a two force member because it has two exertion points. And these two exertion points, you can connect them with a straight line, and that will tell you what is the direction of the force in these two force members. That is a special case one. We call these two force members. The special case number two, that is a three force member. And I give you some example. All right, here, what type of two force member we have? So I do have a two force member here, right? So this is a two force member because it has two exertion points for the reaction forces. So these two forces have to be collinear, opposite direction, equal magnitude. All right, can you spot the two force members and three force members here? Okay, anyone can spot the three force member here. I give them two bonus mark for the mid-semester exam. Who can spot a three force member here? All right, so let's watch them one by one. What would you say about a BC? BC, is this a two force member or three force member? Nima, what would you say about BC? Is it a two force member or three force member? Flynn, Ethan, yeah. BC is a two force member because it has one exertion point here, one exertion point here. And what would you say about the DBA? So DBA is a three force member because it has three exertion points, one here, one there. And then, all right, so because BC is a two force member, I know that the force of B is like that, and D, the force is like that. So if I extend these two forces and they are colliding somewhere at the top, so I know that these forces should collide at the same point, right? So these three forces, they should collide at one single point. All right, can you spot a two force member here? A two force member is the piston, that hydraulic piston AB, that is a two force member. And what else? Um, yeah, AC is also a two-force member, but then maybe that container is a three-force member because there's one force here, and the weight of this one. So the weight CA, BC, BA, there are three forces which should collide at one single point. All right, so I only repeat this once. This question might be examinable. It's very similar to an exam question in the past um, term. So keep an eye on this one. And the key to solve this problem is just identifying the two force member and three force member. So I give you a simple hint, and then you should be able to solve this. So DB only has two exertion points, so that is a two force member. As a result, B is, we know the direction, but we don't know the magnitude. D, we know the direction, we don't know the magnitude. But A, B, C, that is a three force member. One force here, one force here, and A should go through the collision point here. So I leave that one for you to explore because I told you the hint and you have the solution. So yes, that is just one solution. You might solve this with other ways. I mean, you can always break the forces into x, y, and solve that with the Cartesian coordinate, or you might choose the graphical method, constructing a triangle either for ABC or for BD. So now let's move to the three-dimensional cases. So three-dimensional cases, the difference is you have to appreciate the different type of the support we have. And yes, cable, still the forces act axial to the cable. Smooth is perpendicular to the direction of the motion. Roller, perpendicular to the direction of motion, the reaction. Ball socket, it only develops three translational resistance. It's free to rotate in all three dimensions. So when you have a journal bearing, the journal bearing is restricted to rotate in two directions, and it's restricted to have two translations. It is free rotate axial to the axis of journal and free to slide along the axis of the journal. So when it's not a journal bearing anymore if that has a square shaft. So the square shaft prevents this from rotating axially, but it slides axially, right? And then when you have a single truss bearing, a single truss bearing is restricted axially in one direction and is free to slide in other direction. So that is a single smooth pin which does the resistance toward two type of rotation, three translations, and that's a single hinge which does offer resistance toward two rotations and three translation. When there is a fixed support, it's a collection of all resistances, resistance in three translation, three rotation. So now your turn. What type of support is this? This is a ball and socket. It only offers three translational resistance. The next one is a journal bearing, resistance toward two translation and two rotations. This is a single truss bearing, and well, from right to left, axially it resists. From left to right is free to slide. So three translational resistance, two rotational resistance. That is a single smooth pin. So you have to construct the position vector along the axis of the piston. And yeah, so we have a number of solved examples here. And there are two ways of doing this. I mean, some of these problems you can solve them by a scalar form, which is just ignore ijk, but in most of the cases, you would like to construct, first you make a free body diagram. From free body diagram, you write the forces with their ij component, the um, torques with their ij components, and then all you do is you solve two vector equation. The first one is net forces as a vector equal to zero, which that give you fxi plus fj, or rxi ryj plus rzk is equal to 0i plus 0j plus 0k, and that equation can be reduced into three scalar equation. And eventually you have to write net rotation about a point equal to zero. That generally involves writing a determinant, and that determinant, when you write again, you get moxi plus moj plus mozk equal to 0i plus 0j plus 0k, and that reduces to three scalar. Three scalar. Altogether, you will have six equations to solve. So six equations, you can handle a maximum of six unknowns. And that is all we had to um, summarize today. You have 4 hours left with Greg. Please make sure that you participate into the demonstration and tutorial classes. So Greg would take care of examples for this chapter. So most important is the two-dimensional cases. In exam, you might be given some simple 3D problems, but even with the complex one, make sure you summarize the remaining slides and just the selected problem from the worksheets. And if you have any question, don't hesitate sending an email to me. This Tuesday is public holiday, so my consult is on Tuesday, but I will be available this Friday. If you want to see me Friday, you can find me TD 192. Yes, that's okay, Nima. Stay. I will talk to you at the end of the class. So, Flynn, Ethan, do you have any question? All right, so let me just change the status of the Flynn, and Nima and Ethan were already marked as in. Now Flynn is updated. All right, so all good. I look forward to see you next Monday. Nima, please stay in the class. I'll talk with you